My name is Devin Cook. Happy to be here. And today I wanted to talk a little bit about binary exploitation. And since 25 minutes is not a whole lot of time to cover this topic, I'm just going to jump right in. So my background, I went to UK. I'm like fairly classically trained, I guess you would say, in computer science. I've spent like a lot of time in academia. About 10 years in college now. So I got 2 degrees at UK, and I'm finishing up my 3rd from Auburn right now. And one thing that I really noticed is that there's like a real lack of I don't know, what I would call like hardcore security curriculum in academia. So how many of you guys are in college or have been to college, like computer science people? Yeah, so there are not a whole lot of universities that offer like security curriculum, and of those, there are even fewer universities that offer like more offensive security type of courses where you're doing like actual exploitation. You're learning how exploits work. And specifically, like for this talk, we're going to talk about binary exploitation and stack smashing. So this. It'll be a little technical, but you know, it's 25 minute talk, be high level, and my goal here is to kind of leave you guys with some links and places to go where you can go and do your own research and teach yourselves how to do this stuff, because that's pretty much what you have to do if you want to get into binary exploitation. Is you've got to teach yourself. But thankfully, there's a lot of really good material out on the internet. So we're going to talk about basically how smashing the stack works, and this is a method that's been around, you know, for a really long time. And security, as you guys all know, is like really cat and mouse game type of deal, where a lot of times defense is led by the offensive stuff that goes on. So we're going to talk about that back and forth, and we're going to discuss some of the common mitigations for stack smashing that you find in binaries nowadays, and kind of ways to get around some of those. Okay, so let's talk about the stack first. How familiar is everybody with how binaries work in memory and how processed memory space is? Like, has everybody looked at that before? Like head nods, maybe? Okay, so some people not as much. All right, so basically the way it works is you have a bunch of memory that's allocated to each process, and each process has what's called a stack, which is where these frames here get allocated as functions are called. So these frames have important data in them for the execution of the program. They include like local variables to that function. The arguments to that function are all on the stack. And then also return addresses are on the stack as well, which is really great because if you can overflow a buffer, then you can overwrite those return addresses and hopefully gain control of the execution of the program. All right. Now, the kind of notation that we're going to be using for most of these examples is this fabulous ASCII art that I've pulled from the original Smashing the Stack article from Frack. And what you can see here is the stack actually grows down, so the bottom of the stack is actually the higher addresses in memory. And so there are different what's called calling conventions, and we're not going to get into this too heavy because this is that's pretty technical stuff. But we're just going to talk about one type of calling convention, and that's kind of the standard calling convention that's used in Linux, which is like cdecl. So the way that works is that the arguments are pushed on in reverse order onto the stack, and then you have the return address next, and then the block pointer, which is basically like a saved stack pointer, and then you have all of your local variables, including the buffer that you're hoping to overflow. All right, so these are all laid out in the stack, and remember that memory increases to the right. That means that the beginning of your buffer is all the way over here on the left, and when you start writing your buffer, the end of it is over on the right. So if you're able to continue writing, you can see you'll overwrite the save stack pointer and then the return address. Okay. Okay. So yeah, there have been a whole lot of mitigations that have been introduced, but if we go all the way back to the beginning, we'll just talk about just straight up stack smashing, and this is like right out of the FRAC article. Does everybody know what FRAC is, first of all? Like I mentioned a few times. Okay, so a lot of head nods, but yeah, so it's like a webzine that's been around for forever, and yes, they have like really good articles on it, and there's like the one canonical "Smashing the Stack for Fun and Profit" article that that explains how all of this stuff works. Yeah, it was, I think, in the 90s sometime. But these techniques have existed long before that. That was just like the first kind of like public introduction of, here's how you do it. It's really easy. All right, so the way that stack smashing works is you have a buffer somewhere in your code, and that buffer, you're copying user input into it. And if you can control that user input, you can write whatever you want there. So, for example, you could come up with shellcode, which is basically just binary instructions that can be executed by the processor. And you can continue writing all of those up until you get to the return address here. And then you basically just write a pointer value that points back to the beginning of your shellcode. Which means that when the function returns, it's going to start executing your shellcode. And the way that that works is when a function returns, there's some code that cleans up the stack and gets rid of that stack frame that it was using. All right, so basically a return instruction is essentially just pop EIP. So it pops whatever's on top of the stack currently into the instruction pointer and begins executing there. So there's a little bit of cleanup code that that gets rid of the local variables that you were using, and then puts the stack pointer back where it should be, and then it executes a return instruction, and it pops this value into the instruction pointer and instruction counter, and begins executing there. It does a jump to there, basically. All right. So you can see if you're able to write your shellcode here. Now, obviously, you need enough space to fit your instructions for whatever you want your shellcode to do. So you need a buffer that's big enough. But yeah, so you can write your shellcode here and then essentially just jump to it when the function returns at the end of the function. So that gives you arbitrary code execution. So how can we stop this from happening? Well, I mean, the first easy way is something called a stack canary or a stack cookie. And all that is basically just some value that you put in between your local variables for the frame and basically the return address, right? So that means that in order to overwrite your return address, you now have to smash this stack canary. And then when the function returns, before it pops the return address, it checks the stack canary to verify that it hasn't been altered. Okay, so it keeps track of what these cookies or canaries should be. And if this is altered, that means that stack smashing has occurred. You've overwritten that, and it knows not to jump to whatever this return instruction is, because it could be invalid. All right. Okay. Now, this is actually pretty hard to get around. Your best bet, so initially your best bet was to overwrite some of these local variables that actually occur before the canary. But nowadays these really often get reordered, so your local variables may not be directly after your buffer. It'll put the buffer right next to the canary. And that makes things a little bit more difficult. However, one thing you can do is these stack frames are stacked on top of each other. So occasionally you're able to just rewrite several stack frames and then overwrite some local variables in a lower stack frame. And that can occasionally get you control over, over execution of the program. Okay, and then, so Windows does kind of a similar thing, and this is something that's Windows specific. It's called structured exception handling. And essentially the way that it works is kind of similar to stack canaries, except that it stores some pointers on the stack here that tell it like where to jump to when something goes wrong. But it turns out you can actually use these to gain arbitrary execution anyway. So thanks, Microsoft. So yeah, and the way that you do that is these exception handlers are kind of structured like a linked list, and it'll execute one and then jump to the next one. So you're actually able to overwrite the pointer to the next one and point it into some shellcode that you control. All right, so how can we stop this kind of stuff from happening? Well, so if you see here, like you still have your shellcode on the stack. So if we mark that region of memory as not executable, then you end up with something like data execution prevention or the no execute bit, right? Now, this is a picture of the whole process's memory space, right? And the stack that we've been talking about here, the program stack, is just this one piece of it. And you also have the heap, which you guys have heard about. We're not going to talk about it much today, but heap exploitation is another topic entirely. But yeah, so there's a lot of stuff that's accessible here and in the same memory space. So do you guys see anything in this that maybe we could abuse? I mean, like if you look in this region, the memory mapping segment, it might be a little bit difficult to read in the back, but basically any libraries that you load, for instance libc, they get loaded into this address space here and they're accessible. So that means that these need to be marked executable. You need to be able to execute these because they're program code that could be called by your functions. So that means if we're able to return into these libraries, then we can make it behave how we want it to behave. So that is something called a return to libc attack. And return to libc is great, but it relies on you having existing code. And it turns out, like, for instance, the libc library is huge. It's got like 2,000 subroutines. So there's tons of code for you to return to. And you don't even have to return to the beginning of a function. You could return, into the middle of a function. You just have to overwrite that return address with whatever address you want to start executing at. And basically, all that needs to occur here is you need to set up the state to a certain like known value that your function that you're returning into expects. Okay. And yeah, so the way that this works is you overflow the buffer in the same way, but for your return instruction here, you just have a pointer somewhere into libc. So yeah, so and as soon as your function that you're currently in and that you've exploited, as soon as it returns, it jumps into libc and begins executing wherever you tell it to execute. So that's pretty great. So this whole thing kind of introduces the concept of return-oriented programming, which you may have heard of before. It's really useful because it can be hard. So for instance, like if you get rid of libraries that are usable, like in your map, like libc or whatever, if you don't compile against libc, then that means that you can't jump into there. But your program is loaded into memory still. There's still code that's in your program that you could jump to. So there's this concept of gadgets, which if you look over here on the right-hand side of the screen, a gadget is basically just one or two instructions followed by a return instruction. And these gadgets just do very simple things like, maybe a push to the stack, a pop to the stack, or some simple arithmetic, and then there's a return instruction. Now, it turns out you can string together all of these gadgets into essentially a language that's what's called Turing complete, which means you can do anything with it. And there's actually a compiler called ROP-C that you can write C code, essentially, and you compile it into gadgets. So they found out that, like, given a certain number of gadgets, you can do whatever you want. So that's pretty cool. So, and there are also tools available that you can run, like, on libraries or on your binary that you're exploiting that tell you where all of the gadgets are in your binary, what addresses they are, and what they do. But yeah, so the way that ROP works is you essentially write what's called a ROP chain, which is basically just a bunch of different return addresses that you want to execute in order, okay? Because remember that a return instruction is basically just pop EIP. It just takes whatever is on top of the stack, puts it in the instruction pointer, and just begins executing there. It doesn't jump to there. All right. So so let's say, like, this here is the address of your buffer, the beginning of your buffer. All right, and you start overwriting that buffer. Okay, and you overwrite it all the way down to here. Here's the end of the buffer, right there where it says saved EBP. All right, and you also smash that, and then this value here is your first return address. And if you set this return address to the address of one of your gadgets, as soon as your function returns, it's going to pop that into memory, right? And it will execute this XOR and then return. And when it returns, the next thing on your stack, since you've just popped this value, is the following return address. Okay, so what you've just done is you've overwritten not just the buffer, but also the saved pointer and everything beyond it with your ROP chain, which is just a list of return addresses to execute in a certain order. All right. Now, so let's just say that your goal was to set. Now, commonly ROP is used to to set up a couple of registers to specific values, and then execute like an int80 or a system call in Linux. And the way that you do that is you can have some math that sets, like, say, for instance, your EAX value, which is what tells it which system call that you want to call. So, like, for this example, if we wanted to set EAX to 4, and then we wanted to store a couple of just arbitrary values in EBX and ECX, which are two other registers, then this is the ROP chain that we would use for that. So we have the address for the first gadget, which does an XOR EAX with EAX. Who knows what that does? If you XOR a register with itself. What's that? Yeah, it clears it out, so it makes it 0. And then the next gadget in the list here is just an increase EAX. And you see that we have this, this address listed multiple times. Okay, so we call it 4 times. We increase EAX 4 times, so that means it's 4 now. So that's our first goal, done. And then we can see the next address on the stack is the address of this gadget, which happens to be 2 pops and then a return. So if we just write whatever arbitrary values onto the stack that we wanted to store in the registers, once it executes those pop instructions, those will be loaded into the registers. Okay, so it's just a matter of finding the right gadgets that you need to set up your state to whatever you need it to be in order to call your system call or whatever. And one thing that ROP is commonly used for is to re-enable the execution of your stack space. So yeah, so you can call a system call that says make my stack executable again. So that just takes like a few ROP instructions. You just have to set EAX to the correct value and then set the parameters correctly, like I think a few nulls or whatever. And then you run an int80 and all of a sudden your stack is executable again. Then your next value here can be a pointer into your shellcode that you've also written on the stack. Okay, so so that's pretty great. Okay, now how can we make this more difficult? We can do something called address space layout randomization, which means that these random offsets are included, which means that your stack, all of your mapped libraries, and your heap will be at random addresses between runs. Now, there are various ways around this. Like if you're on 32-bit, the amount of entropy is sometimes small enough that you can just brute force it. And you may have to run your exploit a couple of times, but it'll usually work. When you're working with 64-bit, it's a little more challenging. You usually have to find what's called an address disclosure vulnerability to use in conjunction with it. But yeah, so that pretty much brings us up to the current state of how things work. So if you look at a modern binary, you'll see usually like dep or nx turned on. You'll see stack canaries. You'll see address space layout randomization. Now, there are a couple of mitigations that make things easier on modern systems, like sometimes shared libraries have ASLR disabled for whatever reason. Like I think last year there were a couple of blog entries published about Dropbox. The Dropbox libraries were ASLR disabled, and if only one of those is disabled, that means that an attacker could use ROP to exploit your process. But yeah, so it goes back to the whole like the defenders have a much more difficult job. The attackers really only have to find one vector in, whereas the defenders have to try to prevent everything bad from happening. They have to do everything right, and even so, if the attacker is able to find some kind of undisclosed vulnerability, then they can still get in. So, all right. So where to go from here? There are a couple of resources for online training. I actually gave like a much more extended version of this talk for a buddy's course, Owen Redwood. If you go to DEF CON, you might have seen him. He's got an enormous mohawk. He's around usually. And then he goes to FSU, and he teaches an offensive security course. And he actually published all of his curriculum as he like released it under a Creative Commons license. So there are other universities that are using his material. And also, if you Google my name, you can find my blog, and I promise I will post a link to this this presentation so that you guys can get the links. Yeah, so opensecuritytraining.info is also a really great one. There's a ton of material there and a lot of videos. It's all really good. And then I highly recommend getting involved with CTFs if you're interested in this kind of stuff. There's the DerbyCon CTF going on right now, which I just came down from. I'm fighting my afternoon hangover right now because I stopped drinking a couple of hours ago. But I'm going to BourbonCon tonight, so all right. Yeah, so I highly recommend doing CTFs. They're a lot of fun. You meet some really smart people, and you'll find a lot of times that the environment in these CTFs is really engaging, and like people are there to help people and teach them. So it's a really good time. So if you don't have a CTF team, start your own. Just gather a few people around and start solving some problems. And there are some really good links here as well. Like microcorruption has a really wide range of challenges, these war games that start really easy and then get more difficult. And ctftime.org has like all of the upcoming CTFs listed. And then these top two links, like worldwide actually, yeah. And a lot of them you can participate in over the internet. But yeah, and then these top two links here, the Shellstorm and the GitHub link, are for archives of past CTF problems and write-ups. So those are really useful. You can go and read about problems and how other people solve them. So, all right, I think I'm out of time now, but yeah, I promise I'll post this link. If you just Google me, you can find my blog. It's kind of, I haven't updated in a while, and it's kind of bad, but yeah, you can find me. So thanks, everybody. And if you have questions, I'll be around all weekend. Come talk to me. I'll be probably in the CTF room drinking a lot. So, yeah, buy me a beer. There you go. Excellent. All right, thank you guys.